right, sure. So the tool I'll be demoing is a tool called Magic Trace. So we heard a little bit earlier today about processor tracing, and processor tracing is very cool. But I have never particularly been a fan of the perf tool, honestly. I think it's very complicated, and the visualizations are all there are visualizers, I guess, but like a lot of the visualization is on the command line. I like seeing stuff, in some sort of app or something where you can see the data. You can like kind of manipulate things in your head, in 2D sort of thing. So Magic Trace, what it is essentially a front end for Intel processor trace to get detailed function execution for your programs, right? So the idea is that it's taking the kind of Intel-specific format, decoding that, and then converting it to like a trace format which is easier to visualize. Specifically, the format they chose was the Fuchsia trace format for whatever reason, well, I think I know one of the reasons, but for whatever reason they chose the Fuchsia format, and it's an open source project from Jane Street, and there's a little bit of a README and stuff about what it actually is, right? So let's take a look at like what actually looks like. So in reality, it's just a binary that you're basically going to wrap another binary. So for example, in this case, I'm actually wrapping the trace processor of Perfetto, and I'm opening this trace, right? So I can run this, and it prints an error about timing granularity, whatever. And when I Control C, it stops the trace at that point, and it writes it to this. If I do ls, ls. Trace.fxt, like this file here, that's the trace generated as a result of this, right? And the cool thing is that then you can take this trace and then open it in the UI. And so this is the Magic Trace UI, then what you're basically seeing is a function called graph, right? And this is not sampled or anything. This is the real-time execution of this function while I Control C in trace processor. So you can see it's like over 650 microseconds or something. It is very constrained because, as Al kind of mentioned, it's high throughput, a lot of data very quickly, and so they can't really get like massive timelines. But the granularity you get is like on the order of tens of nanoseconds. So like you can see like 300 nanoseconds or so, and there are other smaller slices even still. So it's not just when you Control C. You can also like instrument like your binary with like this stop indicator function. You can define this function extern C, like the Magic Trace stop indicator, and then whichever function that you want to stop the execution in, you can just call that function, and then Magic Trace will kind of hook into that point. That's pretty much Magic Trace. The cool point, it's actually just the Perfetto UI reskin, so you can open the same trace in the Perfetto UI. But yeah, that's everything about Magic Trace, I think. Yeah, thanks. Yeah, I haven't. Okay. Hello? Oh, okay.
Hi. So KCacheGrind is a tool that was developed back in 2011, 2012. So it's a bit a legacy, but it's useful, and especially for the guys here that are interested in low-level profiling. So when I mean low level, I mean line level, not assembly or anything, but also assembly. So for example, we have this program, and so we have like a main that calls easy and hard, and each one calls work with a certain counter and causes a job to be done, to be spinned for a number of iterations. So now we compile it and we run Valgrind on it. Valgrind is a virtual machine that allows many types of checks on the software, memory leaks, etc. And one of the tools can generate a callgrind. So callgrind is a very simple textual format that you can generate easily from any type of thing you're doing, and then you can open this on the KCacheGrind view. So here is how the basic Kcache wind looks like. Just a second. Okay. It's refreshing or anything. Okay. So, yeah, that's not the basic one. So you can see a list of, on the left you see a list of functions with their cost, self-cost, and inclusive cost. And on the right, you get the various displays. You can look at the call graph, very useful for some of us. And you can also see source code and machine code if that's enabled. It requires some configuration. So that's the tool itself very quickly. Like there are many features here, but I guess those of you whose see it as relevant can go out and check it. Another thing we did at my company, one of the problems is you have those workers, but you cannot really know how much work each worker did in each context. So you don't know that worker 1 worked harder under project 1, and worker 2 worked harder under project 2. So you see their cost, but you don't see how it's associated. So Valgrind has a flag that's called separate colors, where you can define the stack that you dump and the depth of the stack. And then you get this long function names along with their colors up to the root. And in Mobileye, we added, and I offer it if anyone wants to pull it, because I haven't been able to upstream it to the project itself. But if anyone wants it, he can contact me. We added the capability of seeing the, so let's open it. It's this one. So now you see we were added with arrows. So we can open each worker and see how much it costs under each context. So now you can see costs of functions in their full context, and you can drill down. So going down in the tree view actually goes up in the calling order, and you can also see that on the graph. It changes significantly what you're looking at under Kcache Grid. So it needs to be considered in each and every case, in each and every view you're looking at a function at a specific context and not in global context. So that's it. Thank you.
Cool. So yeah. And they will be talking about.
I'll be talking about the tools that you could. I plan on actually having. Oh wait, well that's right. I don't need to plug anything in. I forgot. I just have to do this. Let's see. Entire. Share it now. Oops. Can we see it? There we go. So just some tools. I'm like said, the libtrace event, libtrace command, all that stuff. I'm going to actually have a tools directory within the trace command directory, and here's some of the things I've been working on. So if I were to do trace command, record -e sched switch, I could. There we go. And on my, I have a function. This is a scheduling migration test that I'm running. It's going to run. I'm going to record it, just scheduling switch. Hit there. Now I get all the data there. I'm going to go to the so I just copied that trace.dat file they just created here. And one of the tools I have is called, so first of all, kind of show you what it is. This will be all in the trace command eventually tools directory. Task, what was it called? Task time.c. So basically it just kind of will read all the scheduling switch. It's not that big of a code, and it's still kind of debuggy. So if I do task time.c, I want to do migrate on the temp, get rid of that hide. Demo trace.dat file. And whoops, let me do a less on that. So what it does is it shows you, it looks at the state when things are scheduled out, scheduled in. So it tells you here's all the time, the total time it actually was on the CPU, how long it was preempted. Now there's several threads that are running, so you'll see that the first one's just all the times. It tells you how long it was blocked. It didn't get blocked at all. Blocked on I/O. So if it schedules out blocked on I/O, it tells you how long. The sleep, then it does it per thread. And if you, the first thread shouldn't be preempted very long because that's like it's the running thread with the highest sort of the highest priority. Then the other ones are, they go lower in this is low priority back to high priority again. So this is actually the highest priorities down here. So you notice it never got preempted. So it actually is working, the second priority only got preempted for a little bit. This one got preempted for more. This one got preempted for more, even that. So it kind of shows you like how things are working. So that's one of the little tools if you're interested in one task one. Another little tool that I'm going to have with the same thing using the libraries is this time I'm going to do the same, let's trace the same thing, but this time I'm going to, instead of tracing schedule switch, I'm going to do function graph tracing and record function graph. I'm going to probably lose a lot of events because function tracing does lose a lot of events. So now I'm just function graph tracing, hit record the all things. Now I'll copy that down. And my next one I have like same thing. If I do, I think it's called trace flames or something. That I'm going to make this into a library function that's going to override it, but it's got a lot to work. It's still buggy. But I'm going to do basically trace, I think I have it already. Trace flame. So yeah, if I do the trace that file into, what it does is it will convert it into Brendan Gregg's flame graph utility. So then I could do the flame graph here, take that file, put it into a thing. If I do QIV, actually, what's probably even better is if I do the, if I find that file here, it shows you the flame graph, which you could see actually. I could click, what is that guy? This is called exit to user. This is probably because of the RetPolines. It takes a long time. You can see how much it longs to take that. But then this is a, whoops, go back to reset. So if I just, you could pick on these things here if I can, get down there. You know, this is actually something that's, the SVG file you can actually put into any browser and look at it. So little things I'm working on and eventually be in the tools directory. So thank you.
I think Douglas is going to take over the presentation, and they're going to be next up, and they are going to be presenting Lisa.
Okay. All right. Hello, everyone. So I'm Douglas. I work at ARM in the team that deals. Sorry, I think I did. Oh, sorry, I missed one. All right. So, yeah, so I work in the team that deals with the kernel scheduler, and I'm basically developing this tool. So that's a Python API that allows you to mostly deal with trace.dat files and do some analysis on it, and some plottings, things like that I will present. There's another part to this library, which is making experiments so that the tools that we support are oriented for scheduler development. And then collect the trace files and the message output and this sort of things. So we use it both for very customized experiments on like your own machine, like for developers in the team, but also for testing in the CI on some board farm and this sort of things. So the main interface to it is Python notebooks when you're trying to run it on your for your own experiments. So here you can see, for example, that we open a trace file. We do have a way of capturing information from the running kernel, like on the board, that would be relevant to any sort of analysis you will do, which means you can process the trace even if you lost access to the board. For example, if it was in a board farm, you will still be able to run code that needs to know the frequency domains, for example. That's part of the API. So here we have some ways of listing all the tasks, for example. And then we can get into analysis. So it comes with prepackaged functions. So here we are here we're plotting the utilization signal of a task that we defined earlier here, this small 2,4. So that's a trace from a test. So you get bokeh plots that lets you see what was the utilization over time. That is invaluable when you are doing scheduler development, because if you have quirks on that, things you don't expect, there's probably something going wrong or something you misunderstood. And that allows you to very quickly check your assumptions against the real world. Some variants of that. There are some plots that kind of reproduce what you have in kernel Shark, because that is a pretty good way of displaying what's happening in your system. So here you have like a lane for each CPU, and then you have which task was executing. So here you can see like that was the small 2,4 task, this color. I will get to it later, but one of the big use of that is combined with another plots, and you can see the synchronized view with another plots. You also get access to the events here, and you can see where it happens. That's supposed to be two-way. You're supposed to click on the plots, but after some updates, apparently in the latest version of the plotting library, that seems to have been broken. I'll have to get a look at that. So here we can see, if I zoom in, so you can have both something that tells you have a high-level view of what's happening on your CPUs at the moment, and at the same time track the signals. Sorry, that's what I was describing. And at the same time have the signals that you're tracking, or like plotting any sort of custom data that you manage to produce in a pandas data frame, for example. And at the same time, you still have the cursor that gets synchronized between all the plots. Yeah, so that's basically it.
Great,
Thank you.
Okay, so Olivier will take over the presentation. Cool, and they will be presenting Babel Trace, right? Yes. Great.
Is your screen working now, or so it's supposed to be shared on my end? It's not there? It's presenting right now. You're presenting to everyone. Can other people see it on the Google Meets, my screen? I mean, yeah,
Try to show something else. What do you?
I'll just stop presenting and represent again to see the entire screen. Always had problem with Google Meets. Is it working or not? It's presenting, but
Try to stop it.
Is it not there?
Stop it and do it again.
Yeah, we can see him presenting on this. We only see the web browser.
yeah, but I'm presenting the entire screen and allow.
Yeah, and then minimize it.
No, it's still sharing. No. This is still saying he's sharing. I'm still sharing.
Oh,
Fine, you can have
that's why now you see my terminal. Okay,
All right, nice.
good. All right. Well, as someone that's doing computation in the terminal almost all the time, I'd like to have a tool to allow me to do trace analysis within the terminal without leaving it. So I will present Babel Trace. So the Babel Trace allows you to define sink, source, and filter to do analysis on your trace. It's a C library, and there's Python bindings that will show how you can make your own script to do the analysis. So the example I will be showing is a trace of Jammy, a software I'm working on, and I want to trace the ICE transport communication, the packet that are sent over the network, but also the schedule executor. So this is just an example of a script to analyze the trace. It's really just a standard Python script with a main function, printing the histogram of the packet sent on the network, and doing all here the aggregation of different events that's happening in the trace. Okay, I won't go into the detail. If you want to know more about that, you can read the doc. If we look at just the trace, Babel trace comes as a command line tool, and it has the default functionality that's called convert. And when you pass it a trace, it can be any CTF trace, but in that case, it's a LTTNG CTF trace. And if we look at it, we get all the trace one at a time on the line. We can see that, well, you have the host here, Laura, and we have the timestamp. We have the signal, for example, that was emitted in Jammy. We have the CPU ID, and we have the virtual thread ID because I've asked LTTNG to add this context to the event. Now, maybe I'm not interested into the signal, but I'm more interested into, for example, the ICE transport. So I usually do that kind of stuff with Hawk just to filter trace quickly. So now I can just see the ICE transport, and I can, of course, just select the field that I want with Hawk just to do quick analysis like that. But for real analysis, I use the pattern script. For example, I'll show you just the example here. This is the histogram of the trace. Okay, the script I show you in Python will just do that here. And for example, if I'm interested in something else like the schedule executor, well, I can have that too. For example, here. So this is a different event, and I've generated some different information there. And yeah, it's really nice because I write a script for the team, and people from my team can use the script just to see like analysis, like what's the distribution of packets that was sent for the ICE transport, for example, for that thread. And that's it.
Matthew, take over the presentation and be presenting Trace Compass after I twisted their arm.
Yeah, okay, that works. Okay, so a small demo about Trace Compass. So it's a trace viewer graphical interface that can be used to view LTTNG traces. It also supports various other types of traces. So here, I mean, just to show a little bit, so this control flow view, so you can have a look at what is happening in the system. So here I was kind of tracing Grub a couple of months ago, and that was after I've done some modifications to the Grub script to remove a quadratic algorithm in there. So your future Grubs should be faster to update your list of kernels. It turns out that using bash script to kind of put the kernel in the right version reverse order can take a long time if you do it quadratically, right? Okay, so that's after I fix stuff. So I have Grub in there. So actually, the fun thing is, by default, it's going to show you all threads, even the inactive one, right? So, I mean, if I have thousands of small processes which are launched, I mean, those are all bash scripts of the 10 Linux script in Grub. So it takes a tremendous amount of real estate. And I'm really glad that they added this. So active threads only. So as you zoom in, you remove everything that's inactive. So it really allows you to figure out what is happening where. And this nice feature is also this critical flow view. So you just have to know how to enable it. So you have to kind of right-click on a row of the control flow, follow this one, and then it's going to update this critical flow view at the bottom. And this is following the wait and wake ups. So it's actually calculating the graph of what you're waiting for from your point of view, and then it's showing it. So that's really, really, really useful. Yeah. So there's various things. Various things like system call latency. So you have a breakdown by system call. I kind of noticed that they did not do yet the part that I really would like is kind of having that synchronized with the selection. So you could select a range and it will do the statistics computation for that range. They still haven't done it, so it's for the whole trace. But I mean, it's so close, right? So system call latency. So that's interesting. When you click on a system call, so you have the latencies, but then if you go to the event view, so this is like the Babel trace output, right? It's actually highlighting all the events that belong to this system call. So things are really kind of nicely synchronized there. So you can have syscall latency, CPU usage. So there are various small views. So CPU usage is interesting as well. So you can have your breakdown, what contributed to your CPU usage in what you're looking at, as well as a graphical view there. I'm not an expert of those trace viewer tools anymore. I'm really just a user. So, things, yeah, that's quite useful to kind of dig into what is happening, especially when you get a good idea of, okay, the surrounding around here seems to be kind of my culprit. So what is actually going on? So that's what I have. Yeah. I hate those. Yeah, so as I understood it, so what I would expect personally as an end user would be the blocking, right? You wait for something, you're being awakened, and then you can continue. So I'd kind of like to see those arrows meaning that, but as far as I know, the meaning here is I'm following the flow of a CPU. So the CPU is moving to different threads, and I hate that. I always remove those. But I would really like them to be kind of reused for this wake up semantic. Yeah. Yeah, thanks.
Next up, we have Mirasami, who's going to demo PerfProbe. Great.
Yeah. Thank you very much. Okay, let me share my screen. Yeah, window. Okay. Okay. So my demo is not actually tracer, but the support tool to make it debugger. So that the K-probes and the U-probes events have been there for over 10 years, but most of you may not have used it because the one reason is that this is because K-probe event or U-probe event requires that assembly code knowledge to use it. So that So if you want to put the K-probe inside the function body, so in that case you need to know that the instruction boundary or something like that, and also where the target line is compiled in, and also you need to find that what the registers are assigned to the target local variables or something like that. That's hard to be using that doing that manually. So actually I introduced that PerfProbe to help users with K-probes events. This is actually there over 10 years, but I think you may not know that what is that. Yeah, actually, surprisingly, that even Steve doesn't know that the tool. So I would like to show you what the path probe is. Yeah, so that it's very short. The path probe is the path sub command, so that it shows that you can use it with the path event path tool. And so at first, I think that you may want to, let's say, find that your target function. So with the K probes, the path probe with the K option to the VM Linux, this VM Linux has to compare it with the debug info. And anyway, so hyphen large F command will show you that the summary, what kind of functions symbols already in actually the kernel image, and it can filter the function name with the wildcard. And if when you, for example, find that your target function, you can use that large L hyphen large L to show that which lines you can put the probe. So that this one is show that which one can be probed. And for example, if you want to see that the counter here, then you can check that what variables, local variables, can be accessed here. So that this one is line 14th of the VFS read. So that you can set that and with pass it to the large V variables option. Then you can see that what kind of variables you can use. And then finally you can, yeah, this one is a bit complicated, but you need to pass that a single option with that. So count. Then it shows how you can specify that to specify to the K-probes event like this. Then you will run the remote machine, log into the remote machine, and this kernel debug tracing, and like a K-probes event, or you can use that dynamic events for more generic use case. And dynamic events already defined, and what happens, proof, VFS read and format. Then you can get define that a new event with that. If you enable this one, equal 1, 2, and trace. Then you can see that the counter, event with a counter, like this. Of course, if you have if you want to know that what about that this read field, it has what is set to this read field. You can also check that file FOP and read. Then it returns that how to set that the command, and this need to or symbol. Because that this one is just shows that the value, the address, so that you need to need a symbol to know what it is. Then dynamic event. Oops. Oh, file exists.
Did you test it?
Oh, no, sorry. I need to change the line. Yeah, because there is 17th, so can you see that the offset is slightly different? Yeah, because the line is also different. And then 17th lines enabled, and echo trace. Once I need to remove it. Oh, lead with 0. Oh, okay. Yeah, some lead will be 0. I'm not sure what happened. Anyway, for example, you can see that this one is set sec read on that. Moreover, actually, you can use this for the the different architecture. For example, ARM64. I built the ARM64 kernel on that, and if you run this, you can see that the different, the definition for the different architecture. And just copy it, and this kernel debug tracing, and cat dynamic event. And then you can get the new events. Probe, VFS read, format, and you can use that. Echo want enable. Then here you can see that there are new events on the different architecture. Yeah, that's all actually. So I would like to ask the tool developer to use this command to set up the new kprops event. Yeah. 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 Currently support that are x86 ARM and ARM64, maybe PowerPC, RISC-V or something like that. Yeah.
Cool.
Yep.
Thank you.
Thank you.
Okay, and finally we have Ben, who's going to demo Apple. It's called Apple Instruments.
Yes.
Apple Instruments. Great. So do join and present your screen.
Presenting my screen, hoping for the best. And here we go. All right, there we are. Hey, everybody, I'm Ben Hamilton. Some of you may have seen this kind of stuff before, so apologies if it isn't new, but a lot of the snazzy UXs like Perfetto, I think, draw inspiration from a lot of sources. One of them that was the snazzy state-of-the-art about 20 years ago or so was Apple's Instruments UI. Instruments is their wrapper around a whole bunch of things like dtrace, CPU profile, and other things. This is just a random little Magic 8-ball kind of app. I just downloaded it. You click on it, and it gives you random fortunes. And I wanted to demo a little bit about how that integrates with Apple's trace system. So Apple has a system called Signposts. You can put them anywhere with you can have intervals, which have a beginning and an end, it's kind of like this. You can also have individual events, which can have descriptions. And in pure Apple style, every single parameter has to label whether it's public or private for some reason. So I just put in a dummy loop here where before it prints the answer, it loops 1,000 times and sleeps for what should be 10 microseconds, but might sleep a little more. And same thing after. What it looks like in Instruments. So Instruments is the tool where you can provide on the horizontal all of these different, they call them instruments. So you can have you can have a CPU usage profile. You can have a trace of all the system calls, and you can have these signposts. So you can see these kind of clusters of blue activity here, the signposts that I added to the code. So as a reminder, I have the begin and end, and I have the individual events in there. And so I can look at just the intervals themselves. I can jump back and forth. I got 1, 2, 3 of them. So this was an example where I clicked 3 times during the trace. I can look at the individual events themselves and see loop number 999, 970, and as I move through them, you can see up here, hopefully, we're jumping back and forth. If I'm interested in a range, I can kind of zoom to it, and I can move back and forth between the different instruments. I can see what the heck was this thread doing in terms of system calls, for example. Maybe I want to see what were all the threads doing. So all of those use sleeps in BSD Lantern into SEM wait signal. I can also, if we were actually doing interesting CPU stuff other than syscalls, I could jump in here. Most of these are going to be those log messages and instruments. The log messages go to the system log as well as the instruments. That's mostly what the CPUs are busy doing here. Yeah, so that's about it. But yeah, I mainly want to show this more as a historical artifact, because I do think that a lot of this UI became, I can't speak for the Perfetto team. Okay, good. I thought so. I had never actually talked to Primiano about this before, but I could tell there's a lot of loving drawing inspiration from the old the old school when it comes to the Perfetto UI. So you can kind of see a little bit of that. That's about it. But yeah, there are many, many, many instruments. I'm not going to go into all of them, but I personally love being able to see all the system calls and watch where the latency comes from and jump back and forth, and being able to add signposts on top of them to have actual traces with metadata on top of it makes it somewhat comprehensible to the individual developer. That's it. Any questions? Anybody want a fortune? All right.
Cool.
Thank you very much.
Awesome. Okay, thanks, Ben.